All right, 6.1, antiderivatives and indefinite integration. So this is a totally new concept, but related to what we're just doing, in that it's basically the opposite of what we were doing. So we'll get into that and dive into this throughout the chapter. So a function f, note the f is capitalized, is an antiderivative of lowercase f if f prime of x is equal to f of x for all x and I. Okay, so that's basically what an antiderivative is, and we're going to go over it more, but it's basically working backwards from, if you're finding a derivative of the function, it's finding the original function. All right, here's two quick examples of finding them, okay? So let's find the general solution of the differential equation y prime of is equal to 3. So I'm giving you a derivative function. I want what the original function was. So what function do you know has a derivative that would be equal to 3? That would be 3x, right? Because the derivative of 3x is 3. Now, we're going to include a plus c at the end. Why? Because our original function could have a constant and we don't know, right? Because the derivative of a constant is 0, which is why it's not included in your derivative function up here, right? So by having plus c, that plus c represents any possible constant number. And we have over here, y prime equals 4x. Now, what original function will get us a derivative of 4x? That would be, if you think back, it'd be 2x squared. Once again, plus c, because it could be a constant up front. Now we're going to briefly dive into our notation with antiderivatives. So one of the things I briefly mentioned when we were talking about derivatives is we can write derivatives as dy over dx, right? So with dy over dx, if we multiply both sides by dx, you get dy equals f of x times dx. Now, if we want to find out what the antiderivative is of f of x, one way to write this is a symbol, which we're going to hold off on. We want to know what the antiderivative is, the symbol being this little weird curvy s. Okay, by using this symbol and this tells us that we need to find the antiderivative of f of x with respect to dx. That's how it's read. So, how do we find it? Your solution would be f of x plus c. If we're to try to find the antiderivative of f of x, all we would do is work backwards like we did with the other two problems we did on this page and add plus c at the end. All right, on this page we have some basic integration rules and your differentiation. I color-coded so that you knew where they were similar. Some of them we kind of already did in the last one, like when we're integrating 0, just put a c in its place. Always do. Constant. Anytime you integrate a constant, just put it's just going to be k times x plus c. And the value k times a function, you can always move it outside of your integral and then integrate whatever your function is if it's easier. The addition and subtraction of two functions, you can separate them as two separate ones. Sometimes it's going to be easier for you. And the big one right here, remember the power rule? Back when we did derivatives, put the n up front and subtract 1 from the exponents. This is the opposite, remember. So with integration, you're adding 1 to the exponent, and then you're dividing by whatever your new exponent is. Okay? Pause this, write this down. We'll do some practice with some of these. Let's do a couple examples here. So we have the integral of 7x dx. So we can move that 7 up front if it makes it easier for you, which might not be a bad idea. And then the antiderivative, add 1 to the exponent, so it's 2. And then we're dividing by our new exponent, which is 2. Remember, plus c. Okay? So 7x squared over 2, or you can write it like this, 7 over 2x squared plus c. Either or works. With this one to the right here, it's easier if we change it to the negative second power, okay? The fraction thing makes it hard, so we can't really do too much with it. So if we change this, it's a little easier, because then I can add 1. So it's negative 1 divided by our new exponent, which is negative 1 plus c. So our answer is simply negative x, or if I have the dx here. There should be a dx when we are integrating right there. So negative x to negative first plus c. We can write this a little nicer, throw that in the denominator, so we negative 1 over x plus c. All right, one more example, and then we're going to the next thing. So since we're addition all the way in between these, we can do these one at a time, and so we're going to have 4x, add 1 to the exponent to the fourth, divided by the new exponent, plus 5x to the third, divided by the new exponent, 3, plus 4x to the second, divided by new exponent, which is 2, and of course our favorite plus c, that we now know and love. Simplify these, so we x to the 4, 4 over 4 is just 1, so yay. 5 over 3, can't simplify that at all, darn. 4 over 2 is just 2, so it'd be 2x squared plus c. There's your solution. So we just have to do those one at a time. All right, this falls under our initial conditions examples, okay? So I'm giving you that f prime of x is equal to 6x, and that f of 0 is equal to 8. So we need to find the antiderivative of 6x dx, okay? Our goal with these problems is to find out what c is actually equal to, which is kind of nifty, okay? With our initial conditions problem. You'll definitely see a few of these on your assessments for sure. So, we need to find what f of x is. F of x is equal to the integral of 6x dx. We solve, so it's going to be 6x squared over 2 plus c. And that simplifies to 3x squared plus c. We plug in, and then we need to find what f of 0 is equal to, right? And f of 0 should have an output of 8, right? Because that's what we told in the beginning. F of 0 is equal to 8. So we set it equal to 8. 0 squared 0, 0 times 3 is 0, and then we got c is equal to 8. So what does that mean for us? Well, what does that mean? That means c is equal to 8, and if we were to find what f x is, f of x is equal to 3x squared plus 8. So we just solved for our c value. I appreciate you watching, and we'll see you in class. Bye-bye.